Hello friends, I welcome you to my lecture on Euler's equations 2. Now here we shall be discussing the two examples where the functional involves several independent variables which depend on a single variable like the article which we have done in the previous lecture. So these examples are dependent on that. So find the extremals of the functional I by x zx equal to integral 0 to pi by 2 by dash square plus z dash square plus 2 by z dx. So here by and z are two dependent variables that depend on a single independent variable x. By dash is dy by dx, z dash is dz by dx. So here if you compare it with the standard form x1 x2 f x y z by dash z dash dx, we have this. So here f x by z by dash z dash is equal to by dash square plus z dash square plus 2yz. Now the necessary conditions for the extremum of I are, so here in the article we have taken by 1 and by 2 as the two dependent variables that depend on a single variable x. Here instead of by 1 by 2 we have by and z. So we have the differential equations as delta f over delta by minus d over dx delta f over delta by 1 dash is equal to by dash equal to 0. This is one equation because by 1 is equal to by here, and then the second equation is delta f by delta z minus d over dx these are the two necessary conditions for the extremum of I. Now let us find delta f over delta y. So here delta f over delta y is equal to 2z, delta f over delta y dash is equal to 2y dash, delta f over delta z is equal to 2y delta f over delta z dash is equal to 2z dash. So let me call this as equation 1, this as equation 2. Then 1 implies 2z minus d over dx of 2y dash is equal to 0, or dy dash over dx becomes by double dash, 2 we can cancel, so by double dash is equal to z. 2 gives you 2y minus d over dx of 2z dash. Derivative of z dash with respect to x is z double dash, and 2 we can cancel, so we get z double dash is equal to y. So we have two equations, by double dash is equal to z and z double dash is equal to y. Now let us differentiate this equation. By double dash is equal to z twice, so by double dash equal to z gives you this is d4y over dx4 dx4. This is fourth derivative of dy, so this is d4y over dx4. This is equal to d square z by dx square, and d square z by dx square is equal to y. So we get d4 minus 1 by equal to 0, where d is d over dx. Now this is a fourth order linear differential equation. where the coefficients are constant. So auxiliary equation is m4 minus 1 equal to 0. The roots of this equation are m equal to plus minus 1 plus minus I, and so we can write the complementary function. The complementary function will be c1 e to the power x plus c2 e to the power minus x plus c3 cos x plus c4 sin x. Okay, now particular integral is 0 because the right hand side is 0, so y is equal to, particular integral is 0, so y is equal to complementary function plus particular integral, which is equal to c1 e to the power x plus c2 e to the power minus x plus c3 cos x plus c4 sin x. Now let us in order to find the four constants c1, c2, c3, c4, we use the given conditions on y and z. The two conditions are for the values of y at 0 and pi by 2, the boundary conditions, and the two boundary conditions are given for z. At x equal to 0, z is 0, at x equal to pi by 2, z equal to minus 1. So we need four conditions to determine the four constants c1, c2, c3, c4. So two conditions we shall get for the two boundary conditions given for y, and two conditions we shall get for the boundary conditions given for z. So let us write the corresponding expression for z also. So we see here that y double dash is equal to z. So z is equal to since z is equal to y double dash, we have first we find y dash. So y dash will be equal to c1 e to the power x minus c2 e to the power minus x minus c3 cos x, and then we have c4 sin x, and y double dash will be equal to c1 e to the power x, c2 e to the power minus x into minus 1, so plus c2 e to the power minus x we have, and then we have plus c3 sin x. Derivative of cos x is minus sin x here, and derivative of sin x is cos x here. So minus c3 cos x it will be, and then we have minus c4 sin x. Y is c1 e to the power x plus c2 e to the power minus x, c3 cos x plus c4 sin x. When we differentiate it, we get y dash equal to c1 e to the power x minus c2 e to the power minus x minus c3 sin x plus c4 cos x. We differentiate it again, we get c1 e to the power x plus c2 e to the power minus x minus c3 cos x minus c4 sin x. Okay. Now y0 equal to 0 gives y0 equal to 0 gives you put 0 for x, you get c1 e to the power 0 which is 1 plus c2, then we have c3 cos 0 is 1, so we get c1 plus c2 plus c3, sin x is 0 when x is equal to 0, so this is equal to 0, and then y at pi by 2 is 1. So this will give you c1 e to the power pi by 2 plus c2 e to the power minus pi by 2, then cos pi by 2 is 0, sin pi by 2 is 1, so we get c4 equal to 1. Now we have z0 equal to 0, so replace here x equal to 0, so we get c1 plus c2 and then minus c3 equal to 0, and the fourth condition is z pi by 2 is minus 1, so z, let us put pi by 2 for x, so c1 e to the power pi by 2 plus C2 e to the power minus pi by 2, and then we get cos pi by 2 is 0, so minus C4 is equal to minus 1. Okay, let me call it equation number 1, this equation number 2, here equation number 3, and this one as 4. We can solve these 4 linear equations for the 4 unknown coefficient constants C1, C2, C3, C4. So if you add 1 and 3, adding 1 and 3, what we get is C3 will cancel out, 2C1 plus C2 equal to 0, we get C1 plus C2 equal to 0. If we add second and fourth, we shall have C1, 2C1 e to the power pi by 2 plus 2C2 e to the power minus pi by 2, and C4 will cancel, 1 and minus 1 will cancel, we will get equal to 0. So here we get C1 e to the power pi by 2 plus C2 e to the power minus pi by 2 equal to 0. Now let me call it equation number 5, and this as equation number 6. So from 5 we get C2 equal to minus C1. Let us put this value in 6. So putting we have C1 times e to the power pi by 2 minus e to the power minus pi by 2 equal to 0. Now e to the power pi by 2 minus e to the power pi by 2 is equal to 2 sine hyperbolic 2 cos hyperbolic pi. So we get 2 sine C1 cos hyperbolic pi by 2. Cos hyperbolic, it is sine hyperbolic. Sine hyperbolic pi by 2. So since sine hyperbolic pi by 2 is not 0, this implies C1 equal to 0. C1 equal to 0 makes it C2 equal to 0. So which implies further C2 equal to 0. Now C1, C2 equal to 0. So third equation 1 gives you, hence from 1 C3 equal to 0. So we get C1, C2, C3 equal to 0, and therefore C1 equal to 0, C2 equal to 0 gives you C4 equal to 1. So and second equation gives you C4 equal to 1. So C4 is equal to 1, C1, C2, C3 equal to 0. So bi is equal to, hence bi is equal to sin x and z is equal to minus sin x. We can see that the values of y and z which we have got satisfy the given boundary conditions. Bi is equal to sin x, at x equal to 0, bi is 0. Then bi at pi by 2 is 1, and it is also 1 given. Z 0 equal to 0 because sin x is 0, and z pi by 2 is minus sin pi by 2, which is minus 1. So this is the solution, bi equal to sin x, z equal to minus sin x. Now let us take one more example. So this time we are given the functional where x1 is 0, x2 is 0, the limits of integration are 0 and 1, and we have two dependent variables x and y which depend on a single independent variable which is t. So we have 2x plus dx by dt whole square, let me put it as x dot whole square plus y dot whole square and we are given x0 equal to 1, by 0, x1 equal to 1.5, by 0 equal to 1, by 1 equal to 1. So we are given two boundary conditions for x and two for y. Now so here f t x y x dot y dot, we have two dependent variables x and y, one independent variable t. So this is equal to 2x plus x dot square plus y dot square. The Euler's equations are delta f over delta y1. So instead of y1 we have x here, minus d over dx will be replaced by d over dt, then delta f over delta y1 dash. So we have delta f over delta x dot equal to 0. This is first equation. Second is delta f over delta y2, which is delta f over delta y minus d over dt delta f over delta y dash, y dot. Now for the given function f, we have partial derivative of f with respect to x is 2, partial derivative of f with respect to x dot 2x dot, partial derivative of f with respect to y is 0, partial derivative of f with respect to y dot is 2y dot. Now, so equation 1 and 2, 1 gives us 2 minus d over dt of 2x dot equal to 0, and 2 gives us delta for delta by 0, 0 minus d over dt of 2y dot. Now this is what 2 we can cancel, this is or I can say 2 equal to 2x double dot. So we have x double dot equal to 1, and here we have 2y double dot equal to 0. So thus we have d square x by dt square equal to 1, and d square y over dt square is equal to 0. Now this will give you, when we integrate dx by dt equal to some constant a, and here it will be equal to t plus some constant a when we integrate, and here when we integrate we will get dy by dt equal to some constant c. So we further integrate this equation, so dx by dt over dx by dt equal to t plus a gives us x equal to t square by 2 plus at plus b, and dy by dt equal to c gives you on integration by equal to ct plus d. Now let us use the given conditions. x0 is equal to 1, since x0 equal to 1, we have b equal to 1, and x1 is equal to 1.5. So 1.5 equal to 1 by 2, then a plus 1. So this implies a is equal to 0, and hence x is equal to t square by 2 plus 1. Now for y, we have y1, y0 equal to 1, y0 equal to 1 gives you 1 equal to d, and y1 equal to 1 gives us 1 equal to c plus d. So since d is 1, we have c equal to 0. So c is equal to 0, d equal to 1. So we get y equal to 1. So we have get the extremal of the given functional as x equal to t square by 2 plus 1 and y equal to 1. Now let us discuss the case of those functionals which are to be extremized and they involve higher order derivatives. So here we shall be having an independent variable x and a dependent variable y and its higher order derivatives, that is by double dash, by triple dash and so on, another derivative of y. So a necessary condition for the functional which involves higher order derivatives of y with respect to x to be an extremum is that partial derivative of f with respect to y minus d over dx, partial derivative of f with respect to y dash plus d square xy dx square, partial derivative of f with respect to y double dash and so on. The term corresponding to the another derivative is minus 1 to the power n dn over dxn, partial derivative of f with respect to by n. Now this equation is called as the Euler-Poisson equation. Now as in the case of the previous lecture, here also we shall prove this condition, we shall find this condition for the case n equal to 2. The result for n equal to 2 can be easily extended to the case of n. Now so let us say that we have a curve y equal to yx which is twice differentiable and satisfies the boundary conditions. So y is equal to y1 at x equal to x1, y assumes value y2 at x equal to x2 and its derivatives at x1 and x2 are denoted by y1 dash and y2 dash. Let eta x be a function which is twice differentiable and it is the second derivative is continuous, so it is continuously differentiable twice and its values at x1 and x2 are zeros. Its derivative also vanishes at x1 and x2. What we do is in the functional I for n equal to 2 we replace by y plus epsilon eta. So then we shall have for the case n equal to 2 I is equal to for the case n equal to 2 we have the functional integral x1 to x2 fx by y dash by double dash. So let us replace by plus epsilon eta and by dash plus epsilon eta dash by double dash plus epsilon eta dash double dash. So then I epsilon is equal to, I will be depending on the parameter epsilon and we will have I depending on epsilon equal to this. Now this is the function of the parameter epsilon and you can see here when epsilon is equal to 0 this I becomes the given I. So I epsilon reduces to the given I for epsilon equal to 0. Now this I epsilon will have a stationary value provided di over d epsilon is equal to 0. So let us differentiate it with respect to epsilon by using the Leibniz rule. So we can write like this. Because x1 and x2 are constants. Now let us say let bi bar be equal to bi plus epsilon eta. Bi bar dash be equal to bi dash plus epsilon eta dash. Bi bar double dash be equal to bi double dash plus epsilon eta double dash. So then when we differentiate this with respect to epsilon, we shall have delta f over delta y bar into epsilon eta plus delta f over delta y bar dash eta dash delta f over delta y bar double dash eta double dash dx. Now this is equal to 0 when I is equal to 0. So we shall have when di epsilon equal to 0, di by d epsilon equal to 0 gives you integral x1 to x2. Now when epsilon is equal to 0, bi bar becomes bi. So delta f by delta y eta plus delta f bi bar dash becomes bi dash eta dash, then this becomes bi double dash eta double dash dx equal to 0. Now let us see, we will now integrate the second term here and the third term here with by parts. So this second term will be integrated once with respect by integration by parts, and this term will be integrated, third term will be integrated twice by parts. So let us see what we get when we integrate by parts. So integrating delta f over delta y dash eta dash by parts, we get delta f over delta y into eta we get this. Now we have assumed that eta x vanishes at x1 and x2, since eta x1 is equal to eta x2 is equal to 0, this term will be 0. So we will get minus x1 to x2 d over dx. This. Now let us integrate the third term twice with respect to Leibniz rule, with respect by integration by parts. So x1 to x2 let us integrate it by parts. So we get delta f over delta y double dash eta dash x we get this. Now eta dash x we have assumed to be equal to 0 at x1 and x2. Eta dash x1 is equal to eta dash x2 is equal to 0. So this will make this term 0, and we will get minus integral x1 to x2 d over dx this. Now let us integrate it once more with respect to x by parts. So when we integrate it once more, we get minus Okay, we get this. Now eta x2 is 0, eta x1 is 0. So this becomes 0 and we get minus 1 square this. So let us substitute the value of the second term and the value of the third term here, and we shall have we then get integral x1 to x2 delta f over delta y, and then the value of this is minus d over dx delta f over delta y dash, and there we have minus 1 square into eta x dx equal to 0. This is what we get. Now, so we arrive at this equation. Now, since this equation holds good for all values of eta x, we must have this equation delta f over delta y minus d over dx delta f over delta y dash plus d square over dx square delta f over delta y double dash equal to 0. So this is what we get in the case of n equal to 2, and we can easily generalize it to the case of n derivatives. Let us take an example on this. So we have I by x equal to zero to pi by 2 by double dash square minus y square plus x square dx. So this is a functional which involves derivatives of second order, and we are given by 0 equal to 1, by dash 0 equal to 0, by pi by 2 equal to 0, and y dash pi by 2 equal to minus 1. Now, so here we have the case n equal to 2. So we shall apply this result. So Euler's equation is delta f over delta y minus d over dx okay, and we are given f x y y dash y double dash equal to y double dash square minus y square plus x square. Let us find its derivatives. So derivative with respect to y, it is minus 2y, derivative with respect to y dash is 0, derivative with respect to y double dash is equal to 2y double dash. Let us put in the equation 1. So then equation 1 gives minus 2y, this term is 0, d square over dx square 2y double dash, or we can say d4y over dx4 minus y equal to 0, or we can say d4 minus 1y equal to 0, where d is the differential operator d over dx. Now it is a fourth order linear differential equation with constant coefficients. So auxiliary equation is m4 minus 1 equal to 0. The roots are m equal to plus minus 1 plus minus I. So complementary function is c1 e to the power x, c2 e to the power minus x, c3 cos x, c4 sin x. Since right hand side is 0, so particular integral is 0, and thus we have y equal to now let us find the four constants c1, c2, c3, c4. By 0 equal to 1. By 0 equal to 1 gives you c1 plus c2 plus c3 equal to 1. By pi by 2 equal to 0. By pi by 2 is c1 e to the power pi by 2 plus c2 e to the power minus pi by 2, and then c3 cos pi by 2 is 0, so e4 sin pi by 2 is 1, so this is equal to 0. By dash, let us find by dash here. By dash is equal to c1 e to the power x minus c2 e to the power minus x minus c3 sin x plus c4 cos x. Or we are given that y dash 0 equal to 0. So what we have, c1 minus c2 plus c4 is equal to 0. c1 minus c2 plus c4 is equal to 0, and then by dash pi by 2 is equal to minus 1. So what we get when we put pi by 2, c1 e to the power pi by 2 minus c2 e to the power minus pi by 2, and we get minus c3 equal to 0. It is equal to minus 1. So thus we have these four equations. We can solve them for the values of c1, c2, c3, c4. So we have four equations: c1 plus c2 plus c3 equal to 1, c1 e to the power pi by 2 plus e to the power minus pi by 2 plus c4 equal to 0, c1 minus c2 plus c4 equal to 0, c1 e to the power pi by 2 minus e to the power minus pi by 2 minus c3 equal to minus 1. So from these four equations it is not difficult to find the values of c1, c2, c3, c4, and you will see that solving these equations we get c1 equal to c2 equal to c4 equal to 0 and c3 equal to 1, so that y is equal to cos x, and we can verify that the solution y equal to cos x satisfies all the four given boundary conditions. Y0 equal to 1, y dash 0 is minus sin x, so y dash 0 is 0, by pi by 2 is 0, cos pi by 2 is 0, so by pi by 2 is 0, and by dash is minus sin x, so by dash pi by 2 is minus 1. So this is the required solution of the given problem, that is the functional extremal of the given functional. With that I would like to conclude my lecture. Thank you very much for your attention.